introduce today I will take over for Professor Karl Leo to talk on our very interesting topic of Leaftronics that was developed nowadays. So our institute, the Institute of Applied Physics at the TU Dresden, we're actually experts in evaporation and printing of organic semiconductors and making novel devices out of it. But a couple of years ago, a very smart PhD student of ours, he was annoyed of all the waste that was made in the labs with all these devices, and he looked in the global waste for e-waste, and he found that there are millions of tons of e-waste generated of electronic waste globally, and even worse is that almost 80% of this waste is untracked. And this made him look for alternatives in the first place, actually for our printing processes, to have alternative substrates. And he came up with what we already saw in the talk from Mr. Wolf from Word. He came up with a leaf. So taking a leaf from nature, and since you cannot print on leaves itself because it has a quite complex structure, and there is the mesophyll and the skin of the leaf, but there is also this vein structure which is in blue, which is a very stable structure. And if you remove all the green stuff in this image, so the mesophyll, which can easily be etched out, you obtain a highly interesting structure which is made of lignin and cellulose. So this lignocellulose quasi-fractal structure, you can resize it to a smaller piece, and this can be used for substrate technology. The most interesting part here is that it is quasi-fractal, as I said, so it is fractal in multiple dimensions, so you go down into the micrometer range where it still can support the cells. And for our purposes, this micrometer structure is then there to support a biomaterial which we want to be biodegradable, to make biodegradable electronics. So this leaf then acts as a reinforcement structure. The scaffold can be easily dip coated in a biomaterial, and then via dip coating with, for example, ethyl cellulose, which is called their EC, you can obtain a very nice and smooth substrate that you can see on the right here. So this is the biodegradable coating, and by using this structure and putting a chitosan layer on top, exfoliating from a glass substrate, you get an ultra smooth surface with a chitosan layer where you can print on top, so the surface energy is very well for printing, as well as the smoothness is perfect for even evaporation of nanometer thin semiconductor layers. Here you can see an SEM image, and what's very interesting for our OLED applications is also that it's a transparent substrate with a transparency almost as good as conventional glass, still keeping its biodegradability. And here you can see the surface smoothness, where the surface roughness is really less than a nanometer. So depositing nanometer thin films is not an issue on top of these kind of substrates. As for the mechanical stability, here the leaf really helps reinforcing the material. So here we have the substrate with the silver printed ink on top, going through multiple bending cycles, and you can see that by bending even the conductivity gets slightly better, but it doesn't break even after 8,000 bending cycles. And thermally, the material is stable up to around 200 degrees. You can see the silver ink also increasing in conductivity up to 200 degrees due to a sintering effect, and then resistance goes high